We have Luca Biferale from University of Rome. He's going to speak to us about equations and data-driven tools for turbulent flows. Luca, it's all yours.
Thank you. Thank you. Can you hear me well?
Yes.
Okay, good. Thank you very much. Again, I apologize that I could not join you there physically. I would have loved. I promise I'll come as soon as possible, if possible. And let me also ask, I mean, did I understand correctly that I have almost a 1 hour talk?
It's a 1 hour talk, yeah. And,
okay,
and
good.
We can have questions during the talk. So if you have questions,
yeah, so please,
just get the microphone and ask the question.
Yes, exactly, because I will not follow the chat. So please, if you want to ask any question, just interrupt me by voice. Okay, thank you very much. So thank you for the invitation. I have prepared today a sort of short or long overview of some tools that have been started to be used by the community in order to solve a problem like inferring the informations in turbulent configurations. I'm going to speak about both data-driven tools and equation-informed, and I'm trying to, I mean, mainly discuss, a few technical questions and a few, I think, promising directions. And in some sense, if you want to introduce the problem in a funny way, is the problem of, as I tried to summarize here in my first slide, the problem to whenever you have data that are damaged, and how to guess either point-wise or in a statistical sense, in an optimal way, how to refill the gaps. And the gaps could be Eulerian, like in this case, or could be in some sense Lagrangian. I mean, along some one-dimensional strings of data, could be text, but could be also, for instance, velocity along Lagrangian particles, in the case that it will be interesting for us. So the question that I would like to discuss is how to move from this situation to this situation where you have fully reconstructed the information that you were missing. I prepared a sort of, as I say, the overview. I will completely skip the introduction to Uriel and Lagrangian turbulence because you know more than me. And I have a couple of, I think, interesting applications about data-driven and equation-informed tools for Eulerian turbulence. Then if I have time, I also have a couple of applications for Lagrangian turbulence, even though in this case, it's still work in progress. So we have mainly equation-informed tools, and the data-driven aspects are still under investigation. Just to give you an idea that is really the extreme of what one can do with a machine, I played a little bit in the last few days with DALL-E, this machine developed by OpenAI to map words into text, into images. And so this is a really, strong jump from an ensemble of ideas, poetic themes, and something that is real data, two-dimensional data. And I played a little bit and asked DALL-E to produce, for instance, a turbulent flow with a watercolor style image, and it produces something like that. Or, you might be more artistic, asking the machine to map a Miro style image of a turbulent flow into a real image, or a cubist style, and you get results like this. So what I'm going to play on the other end today is how to map data to data. So to make, let's say, a smaller jump between the in and out ensemble. And I will mainly, I start by doing that in a Eulerian framework. And so the idea is how well and how much we can reconstruct the missing information in turbulent configurations by using different tools. The tools, as I said, will be equation-based, data-driven, or even, if I have time, I will slightly discuss about both equation-based and data-driven simultaneously applied. The typical question that might be, I mean, of course, you might have different reasons to ask these kind of questions. One reason is the applied one, right? I mean, you don't have the information, you are measuring something and you want to refill. This could be satellite images that can access only maybe some Fourier wave numbers. Could be, PIV measurements that you measure only in in a subset of your points in your domain. Could be many different situations where you miss either real space information or Fourier information, and you want to guess it. Of course, this inferring problem can also be used in a sort of reverse engineering approach. That is, you might understand by comparing different reconstruction in terms of different missing information, what is the importance of the information that you miss. So if it is more important to miss or less important to miss small scales or large scales, or if it's better to know data close to the boundary or in the bulk. I mean, this is a way to ask, in some sense, to probe the sensitivity of your ensemble to some degrees of freedom. So this is somehow, in some sense, the general background. As I say, you can play this at different level of complexity. You might have a reconstruction that is just reconstruction in what I call here real space. So you have probes that measure your field on a subset of points, and you want to guess what you miss. You might have, on the other hand, missing physical information, in the sense that you might miss some components of the flow. So, for instance, this is very happens very often in the real field, in the real applications, in the environment, where you might measure maybe only one component of your flow, and you need to guess the third component. Or you may measure maybe in one plane, you need to guess the component of the field in another plane. You might miss information in Fourier space. This is what people in the computer vision community calls a super resolution. So you have a measurement of your spectral properties only on some band in Fourier space, and you want to guess what happens, for instance, at small scales. So you need to infer and to reveal a gap in the Fourier modes. You might even have the combination of the two, right? For instance, in large eddy simulation, you want to infer the physics of the subgrid tensor at scales that you do not resolve. So you need to both infer, extrapolate in Fourier space, and also extrapolate for some field aspects in that missing region. So the problem can be as complex as you want, in some sense. And because, I mean, our main interest in the group in the last couple of years was in some sense to benchmark different tools, we decided to focus on a few paradigmatic problems and to exploit and to apply different techniques, and eventually to develop new techniques, and to see how much this in painting works. Hello? Okay, sorry. No, I thought there was a question. Sorry. And so let's focus on a specific problem. So suppose we have a two-dimensional image. Could be, the surface of the ocean that you get from one satellite, and that there is a square cloud covering your surface. Or eventually you might compare this kind of gaps with gaps that have a completely different structure, that are simply randomly distributed in your surface, but keeping, for instance, the same damaged area. And the question is, suppose you have this damage or the other damage, the random distributed damage, how good you are in reconstructing the image. Of course, this is it's a not unique problem, right? I mean, most of the time, the field that you want to reconstruct has more degrees of freedom than the data that you supply, and therefore cannot be unique. So in some sense, you need also to define which sense you say that you reconstruct in an optimal way your image. And the game that of course, I mean, we clearly understand even visually that even though the area of the damage is the same between this example and the other example, of course, the task to reconstruct is not the same, right? So the question that we would like to understand is how to quantify these difficulties of the task, and then the success of different tools in getting a guess for what you miss that is as close as possible. And then I will say in which sense to the ground truth. As I said, I will show mainly three different approaches. One approach is it is split indeed in two sub classes. One approach is what I call completely data-driven. Is where I will spend most of the time. And the data-driven means that I will use either a machine, a neural network, so fully nonlinear fit, let's say, or maps from the input data to the output that you want to guess, or I will use some linear decomposition that is mainly based on principal orthogonal decomposition, and I'll try to compare systematically the two approaches. Then I also show you something that try to reveal based only on the equation of motion. So on the fact that in some cases we know the equations that were behind the data that we are analyzing. And then third, I will also show recent suggestions, even though there are not real applications on problems as difficult as the one that I'm discussing today, where we combine data-driven and equation-based tools. So where we combine the information that we know the equations with the use of a neural network. So let me start from the data-driven case. And let me discuss first the newest, then I will also discuss about the proper orthogonal decomposition, but the newest approach is the one based on machine learning. So now the community in the last 4 or 5 years, especially the computer vision community, did a lot of progress in this kind of in-painting for the data that they are interested at, faces, objects, and animals, and things like that. And we tried to see how much these tools are indeed useful also for our community, and then I will share with you a few comments about that. So there are many different data-driven machine learning tools. I will show you one or a couple that are, I think, the most promising and the most used, by the way, by the community. And they are pretty new. This kind of data-driven approach exists in the literature for the computer vision community since 4 or 5 years ago, no more. So the problem for our application can be summarized in this way. You have some inputs data, that is where you measure the data for the framework, for instance, right? Where your measurements are not covered by the cloud. And you want to map this input data to some outputs that is a good guess, a good prediction for how to refill the gap. And how you do it? Well, you map the input that I call US and the output that I call UG, the U generated, by a machine that is, million free hyperparameters, nonlinear functions that connects inputs and outputs. And without entering in the details on how this generator, how this machine is built, if you're interested, we can discuss. What is important to understand is that this is really more than 1 million free parameter nonlinear functions that maps inputs and outputs. And then you need to fine-tune the hyperparameters, the millions free hyperparameters, in order to have a prediction that is as close as possible to the ground truth. So this is going to be supervised training. I need to imagine that I know for a subset of real cases what is the ground truth in the gap. And how do you train this machine? Well, you train this machine, and this is an important thing that it's going to be, I think, interesting for us, for our community. You train this machine indeed by constructing a cost that you want to minimize. That is, you want to fine-tune the hyperparameters such that you minimize some cost. And the cost is split in 2 terms. And this is important for us. The first term is very easy to understand. It's just you want to minimize the L2 distance between the ground truth. When you see T, it means that you know the ground truth. I repeat, this is a supervised training for you must have a subset, a huge subset of configurations to train the machine. So the first part of the cost is simply the L2 norm, the L2 distance between the ground truth and what the machine has predicted. So you ask the fit to minimize the distance point-wise between the ground truth and your prediction. You easily understand that for turbulent configurations and for fields that are turbulent-like, minimizing only this cost is not going to be really optimal. Why? Because unless you really reach the global minimum, that is, you are able to put the cost to zero, then of course you have full synchronization. You will always make a small error, so this cost will never be zero at your minimum. And whenever you make a small error in this L2 distance, it means that the reconstructed, the predicted configuration, it will be very good, very close to the ground truth concerning the large-scale properties that are the dynamical degrees of freedom which dominates the energy. But it might be very different, very wrong for the small-scale properties, because the machine will accept to be wrong at small scales, because the small scales have a very small energy content, and therefore you will make a very small L2 error. So as a matter of fact, if you use only this term in the cost, the machine will produce a blurred reconstruction, which is almost perfect at large scales, but with small scales that are completely screwed. So how people correct these things? Correct these things by adding another cost. So making the system a sort of multi-objective minimization. And the second cost is, on the other hand, a cost that is judging and weighting only the statistical properties of what you generate. So does not try anymore to reproduce something that is close, strictly one-to-one correlated with your input, but it judges only how good the configuration that you produce in the gap are in a statistical sense. How do you obtain this second cost? You obtain it by using another machine. That's why these things are called adversarial networks, because there are two machines. One is a generator that generates something, and then there is another machine that is a critic that helps the generator by adding this other cost to see how close the statistics of what you generate is to your ground truth. So this discriminator, the other machine, is just a machine that knows the statistics of the ground truth. So it has also, it is trained by seeing the ground truth fluctuations that you have in the gap. It sees also the output of the generator, and it outputs a number between 0 and 1, which is a number that tells you how likely the likelihood of the configuration that you show in input of being a possible configuration of the ground truth ensemble. So in some sense, the discriminator is a machine that is minimizing the distance between, it's helping the generator to minimize the distance of the Kullback-Leibniz distance of the PDF that it generates with the PDF of the ground truth. In order to make things converging, you need to play it in an adversarial way. I mean, there are many tricks, numerical and theoretical tricks to make the things converging. But what is the message that is very important is that to make the system working well in turbulence, and I will show you now in 1 second what I mean for working well. To make the system working well, I need to have this multi-objective minimization where I minimize point-like information with statistical ones. Can you still hear me? Because I saw something disappearing in my window.
Yeah, we can hear you. There's no problem. If
Okay,
I may
good.
ask a question on your notation, right? The norm that you're minimizing, what do you call LMSC, the UGP and T? What are those superscripts exactly?
Yes. So P means predicted, is the output of the generator, and T is the ground truth. So I supply some input, my generator produces a guess, this predicted field, And the cost that I try to minimize is how distant in a L2 sense what I predicted is from my ground truth. Okay?
Yeah, go ahead.
But as I said, only this cost, it might not enough to get the turbulent fluctuations and the multi-scale nature of my field. I also need to supply another cost which judges the statistical property of the system without necessarily connecting it configuration by configuration with the input. Then there are also other just
Thanks, Luca. There's one more question.
Yes.
My question is this in some sense analogous to a feedback control system, nth degree, nth order feedback control system, which is used in real-time CFD analysis along with experimental data in real-time correction of CFD results? Are
I will come back to that. I will come back to that when I speak about the equation informed things. And I will show that indeed, I mean, in which sense it is close to something that feedbacks on your data.
Thank you.
So just for completeness, but I don't want to enter into details. This is not the only, this actor-critic structure that I just discussed with you is not the only one that exists in the literature. There are other variation on these themes that are used by the computer vision community, but I would say that the main idea is always based on these let's say bimodal adversarial machines, one that produces a guess and the other that tells how good the guess is on a statistical sense. And then you want to minimize both the one-to-one reconstruction in a L2 sense and the statistical properties. For instance, there are the other machines that are called constrained image generation that are, I mean, just you can see the main idea in this paper. But I mean, if you are interested, we can discuss eventually later about what is this approach. So so in practice, then what you do, as I said, this is of course a supervised, as I said. And you need hundreds of thousands of data to show to the machine to fit these hyperparameters, to optimally fit these hyperparameters. Then you have this, you have a training phase where you show these hundreds of thousands images. You try to minimize the cost. The cost during the training, the learning is going down. And you see that indeed the machine, if you compare the outputs of the machine at different epochs during the training, the machine is indeed improving. At the beginning is refilling with something that is a nonsense, then it looks realistic. At the end, at least by our naked eyes, it seems pretty good. So at the end, at some point you needed to stop to see that when the cost does not decrease anymore, you needed to stop, you freeze the network, you freeze the hyperparameters. You don't use anymore the discriminator because the discriminator is used only during the training. And then you have your generator that has been optimally trained to refill in a L2 sense and in a statistical sense your gap, and you want to see how good it is. So in order to understand how good it is, you need a baseline, right? You need to understand, okay, how good with respect to what? And we used two different, let's say, well understood, if not even though not systematically always applied in our community, tools that are based on principal orthogonal decomposition. The first one is called GAPI-POD, and the idea is very simple and old, and it means it is based on what? It is based on the hypothesis that you know the data everywhere. You have a training set where you know the data everywhere. And if you know the data everywhere on the training set, you can estimate the two-point correlation of your ground truth in the whole domain. If you have the two-point correlation of your ground truth, you can extract the principal orthogonal components, which means you diagonalize this matrix, you extract an eigenset of eigenmodes that are form a basis that is optimal to reconstruct in a L2 sense any field in the whole domain, or to decompose any field in the whole domain. So how do you use these? So these eigenfunctions are given once forever, once you have decomposed this matrix in its principal orthogonal components using the training data. So how do you use these eigenvectors when you have a gap? Well, the idea is very simple, right? I mean, you have a gap. Now you cannot decompose exactly the field because you don't have enough information to extract all coefficients of the decomposition. So what you do is you just try to fit, to optimize the decomposition of these coefficients by minimizing the L2 norm on the data that you have. This is very simple linear optimal regression method. Of course, again, it's in this case, it's highly tricky. Why it's highly tricky? Because you never know a priori what is the optimal number of modes that you need to use to minimize this norm. Because as you understand very easily, I mean, if you don't have enough degrees of freedom in the frame, right, then the problem is ill-defined. If you use too many modes, it's ill-defined. If you use too few, you don't have enough freedom to reconstruct also the small scales. So indeed, you can set the problem as a minimization problem like this, but every time you need to play a little bit some pre-scanning work in order to understand what is the optimal number of n prime modes that you must use for any given framework or size of the framework, so size of the gap, in order to have a minimum error inside the gap. So the idea is, I mean, just in words, you try to have the right decomposition that is as close as possible to your data where you have the data, and then because the eigenmodes are defined everywhere, you also have the extension in the gap. Another method, which is close to this, but it works better, at least in an empirical sense. I cannot prove that it's better, but it works better in an empirical sense for our application, is again based on principal orthogonal decomposition, but it goes under another name that is extended principal orthogonal decomposition. And the idea here is close but slightly different. What is the idea? The idea is that now you use only the information, you initially use only the information in the frame, even in your training data set. So what you do, you decompose the 2-point correlation, but only in the domain where you have the data. When you're going to reconstruct, you are going to have the data. And so you extract the principal orthogonal decomposition on this subset. Once you have the principal orthogonal decomposition in this subset, you know that you can optimally reconstruct any field with a linear superposition of these eigenmodes in the domain where you have the data. Now the problem is how to have the eigenfunctions also in the gap. And here is the idea of the extended DPOD. So what you do, you extend the eigenfunctions that you have in the gap in this way, using the training data. So where you have, for those configuration where you have the ground truth in the gap, you extend the eigenfunctions by using the coefficients that you would use to decompose the data in the framework, but projected also with the field that you have in the gap. So in some sense, this is the natural extension of your eigenfunction in the gap using the data in the gap. If U belongs to the framework, this would go back to the exact eigenfunctions that you have. So what is the advantage? The advantage of that is that in this way, the eigenfunctions will always fit exactly the data in your framework. The disadvantage is that this extension does not define any complete basis in the gap. So a priori, you don't have, I think, any exact control on how good, how optimal you can be in reconstructing in the gap. But these are two linear decomposition tools to infer something in the gap, which are based on a principal orthogonal decomposition. So let me see the results. So here I show you a summary of now what I do. I apply these tools, either the machine learning based or the one based on principal, on POD, on principal orthogonal decomposition, on a new set of configurations that neither the machine nor the principal orthogonal decomposition have used in their training phase. So these are completely new configurations that have never been seen by the different tools. And I compare the output, how good they are in reconstructing the gap. And this is as a function of the size of the gap. This is the normalized size. So you see, for instance, when you see 1, it means that I have only a frame of data that is made of 1 grid point in my numerics, and I ask the system to, in some sense, refill the gap only on the basis of the boundary condition. When L is small, it means that I supply more and more information. So the results, and this here I show you the mean square error normalized. When you see, this is always normalized with the total energy, so it's a number that cannot be larger than 2, I think, if the normalization is correct in this case. And you see the result. The result, I mean, I want to okay, there is, I mean, you know, the machine reconstruct in average by mimicking 10%, 20% error becomes 30, maybe 40% when the gap is very large. So it's very good to reconstruct, but there are a few messages. The first message is that the machine, the generative adversarial network, is as good as the extended POD concerning the mean square error. If I compare the pointwise reconstruction using millions of free parameters and nonlinear functions, is not really better than using the extended POD that I was discussing before. Both of them are always better than the gap EPOD, but still, you know, the linear EPOD is as good as the GAN. The second message that I want to stress is that the distance, this reconstruction is in any case pretty good. Either you use the GAN, the EPOD, or the gap EPOD, because if you compare with the red line here, the red line is a baseline that you would obtain by replacing the gap with a statistically picked random data in your training set. You know, if you don't have any knowledge a priori, if you don't have any fit, and somebody gives you a frame, the only way that you have is to take one random configuration that you have already seen and you refill it in it. So it's just a statistically consistent refilling. Well, in that case, you would get this root mean square error, which is, as you see, much larger than what the machine or the EPOD are able to do. So in some sense, the good message is that the tools work much better than any blind refilling, but the bad message in some sense, if you are coming from the machine learning community, is that it does not work better than other tools already known by the community. On the other hand, the question, as I discussed before, the problem does not end here. Why it does not end here? Because there is not only the mean square error. I mean, it's not correct to compare the goodness of your reconstruction all in terms of the mean square error. You want also to see if the statistics is correct, right? If what you are using to refill, it's meaningful from a statistical point of view for a turbulent guy. And here I show you a few examples. Maybe I have enlarged it here. Yes, here I show you a few examples of reconstruction. This is the case where you have a damage that is small. This is as I say, this is the reconstruction provided by the gap EPOD. This is the reconstruction provided by the extended POD. This is the reconstruction provided by the machine learning. And this is the original, the ground truth. The three reconstruction here have almost the same mean square error. So if you look at the L2 distance, they are almost as good, of the same quality. On the other hand, even by your naked eyes, you see that the machine seems to be more realistic than the others. If you increase the gap, this difference becomes even more evident. You see, the linear decomposition tends to only match the large-scale properties. The machine learning, because the linear decomposition are anyhow based on some L2 minimization only, the machine learning, thanks to the adversarial part, thanks to the action of the discriminator, which gives you an assessment also on the Kullback-Leibniz distance between what you reveal and the ground truth distribution, is always, even if the gap is large, maybe you make a big L2 error because it's difficult to guess the point-wise reconstruction, but at least the statistics is, as you see, very realistic, much more realistic than the other tools propose. So when you combine the L2 error and the statistical properties, the machine learning is definitely much, much better than the linear interpolators. You can quantify this by this statement by measuring the Jensen-Shannon or the Kullback-Leibniz distance between the ground truth and the PDF produced by the different tools, again, as a function of the size of the gap. And you see that the Jensen-Shannon distance that tells you how much the PDF are different. When you have the machine, the GAN, the generative adversarial networks, have a distance that is much smaller, indeed 1 order of magnitude smaller from the ground truth than the linear principal orthogonal decomposition methods. If you don't believe numbers, you want to see with your eyes, I show you here the ground truth PDF, the black lines for the velocity field inside the gap, and the PDF reconstructed proposed by the machine, the generative adversarial network, for different size of the gaps. You see that the machine is always very good, while the extended POD and the GAPI POD provides PDF that are, I mean, the extended POD is not that bad, but still certainly not as good as the GAN. The GAPI POD is very bad. By the way, the GAN learns that the variable, because here I'm reconstructing the magnitude of the velocity, the GAN learns that the velocity is positive definite, while the extended POD and the GAPI POD cannot enforce the constraint in an exact way, and therefore you have also really unphysical tails in the reconstruction. Then you can ask the same questions concerning the gradients, how good is to reconstruct the gradients. I mean, then I don't want to enter. I mean, if somebody is interested, I mean, I can, of course, answer more detailed questions. Let me spend 1 minute to discuss another inferring problem, slightly different, that again, you can attack by using both machine learning tools or principal orthogonal decomposition tools, is the inferring of the physics, not of missing information. That is, for instance, supposing that you have one component of the field and you want to guess the other component. These are two components of my turbulent flow that was selected out of a numerical simulation of a rotating three-dimensional turbulent flows. And here you can ask a different question. I want to infer another component that is in the plane like the first one, so they are strongly correlated, or maybe the vertical component that we know in rotating turbulence is almost a passive scalar, so is strongly, let's say, is weakly correlated with the horizontal component. So you can also ask questions like this, of course, and you can apply the same tools. We did it recently, and I mean, again, with different degrees of success, but we observe exactly the same message that I gave you before. That is, the machine, if you put the adversarial part, becomes definitely superior to linear decomposition, because it's able to guess also the right fluctuations, while the linear decompositions have a very vague understanding of what are the small scale properties of the flow.
Luca, may I ask a question?
Sure.
Is it fair to compare the EPOD and the GAN, as you say, because you told me that in the machine you have millions of adjustable parameter to tune, while EPOD, since is linear, it will be much less. So shouldn't you make the comparison at same number of adjustable parameters? Or maybe this is what you did.
Well, the question is correct. I think it's, I mean, what is fair, what is unfair depends on who leads the game, right? And in some sense, I think it's fair in the sense that your goal is to have a tool that reconstruct what you miss. I mean, the gap POD or the extended POD, you cannot use more degrees of freedom because they are constrained by the maximum number of degrees of freedom is constrained by the maximum number of eigenfunctions that you have, and the maximum number of eigenfunction is that, because you have a linear mapping, is given by the number of points that you have in your ground truth. So I mean, in some sense, yes, I think it's fair. If my goal is to reconstruct, I'm going to use the tool that is more optimal. That's it.
Okay, thank
so
you.
let me move to the other side of this, to the other point of attack.
Luca, there's one more question.
Sure.
Thank you very much for taking this question. You were comparing machine learning with linear orthogonal decomposition. How about nonlinear decomposition? That is one question. I mean, if you do nonlinear decomposition with also having some knowledge of the local flow field between the points where you have data, then of course it will be quite good for machine learning also. It may compare well. And the other question is machine learning. Do you use linear decomposition or nonlinear decomposition irrespective of the number of data, number of grids or nodes you use? That is another thing. And the other question will be extrapolation. Can you really do extrapolation in any type of computation, machine learning, or that will not be quite good, I guess, extrapolation of data?
Yeah, okay, thank you. So I don't know if I got all the questions. So let me ask first the last one. Concerning extrapolation, it's always a tricky question in machine learning, because you need to, if you train with enough flexibility, you get some extrapolation. Just let me give you an example. In this case, in the case that I show you now, one possible extrapolation would be if you move the gap in different positions, right? If you move the gap in different position and you have trained showing enough different position, it works very well. If you don't do that, it does not. It is not flexible. And similarly, suppose you train with one turbulent, parameters, one, I don't know, Rossby number, Reynolds number, and then you change the Rossby number and the Reynolds number. Then again, if you change too much, it will not work well. And let me say that these problems exist also and often in the linear, in the principal orthogonal decomposition approach, where if the statistics of your flow, the 2-point statistics of your flow depends very much on the parameters that you want to move, then the eigenfunctions will not be optimal anymore, and therefore you need to retrain and to re-diagonalize the 2-point correlation function. So the issue of robustness and it's an issue that, I mean, it's difficult to give a general answer. Yes, it is robust or it is not. Certainly, it's a weak point of the machine, of the data-driven approach. The first question about nonlinear decomposition, frankly, I'm not so aware of too many nonlinear methods. Let me say that the machine learning is exactly doing something like that. It's a nonlinear decomposition that you do it in a blind way. I mean, with millions of free parameters, and you don't ask too much about the physics of the nonlinear eigenmodes. You don't want to have that inside, but you use a nonlinear decomposition. Of course, if you add the possibility, to go inside the machine once you have trained and understand what are the nonlinear eigenmodes that you are using, you might learn something about the physics But this aspect of explainability, that is going inside the optimal solution, it's also very tricky. I mean, it's not so easy to understand what happens inside the machine. At least for us, it was not so easy to do it. We tried and we didn't get too much insights. Then there was the second question that I don't remember now. What was the second question? Sorry.
Question again.
I don't know. I asked a few questions. Anyway, if I want to follow on the answers I got, in the gap portion, you assume that you have a training data
May I
set.
suggest, if it's a very long discussion, we do it after the talk?
Okay, yes. Maybe we can postpone. Maybe it's answered during the coming slides.
Okay.
Hmm? Good, thank you. So let me go quickly on the other issues that I want to discuss. Give you at least the idea of a completely different point of attack. That is, up to now we didn't know the equations, but we had a lot of data to train the machine or to decompose in a linear way. Now we suppose exactly the opposite. We have only one data, we have only one configuration, one observation, and we want to still reconstruct. How we do it? Well, we can do it if we know the equation of motion, because the equation of motion is able to produce the ensemble. I mean, the correct, the equation of motions know exactly what is the ensemble. And so what we can do, you can evolve now the equation of motion, perform a direct numerical simulation, supposing that exactly, I repeat, you know the equation of motion, then we can comment a little bit. Indeed, you might even have some lack of knowledge, but I mean, you suppose that you know that you mainly know that it's the structure of the equation that is producing the data, and then you can evolve the equations, but guiding the equation, nudging the equation with the data that you measure. So for instance, suppose you have this two-dimensional slice, you perform your 3D simulation of your rotating flow, and you add into the equation, into the Navier-Stokes equation, a nudging term, a forcing term that is a linear penalization of your flow that you evolve against the data that you measure. Vn here is the data that you measure. It's a subset of the true data that you don't access, but you have only data here, and you can nudge and guide the equation of motion by adding this guiding term. Of course, what is the aim? The aim and the hope is that the Navier-Stokes will be as close as possible to your data supplied, because you have this strongly forcing relaxation term against your data, and because the equation of motions are evolved in the whole domain, will produce also a physics compliant guess for the velocity field where you don't have the measurements, and indeed in the multidimensional volume. What is the price that you pay? The price that you pay is that now you need to perform a real three-dimensional numerical simulation, which, as you know, it's very numerically highly non-trivial, in some cases, indeed, even impossible. But the price that the advantage that you have is that you don't need any training, because Navier-Stokes are already will evolve the flow around your correct ensemble, correct ground truth distribution. If you apply this nudging, I mean, we couldn't do it in a systematic way as before, because it takes, you need to do hundreds of numerical simulations at high resolution. But for those parameters that we tried, we got results that are very compatible with what you get from the machine learning. Again, there is a trade-off. It depends what you prefer. If you have a few data, you need to use the equation. If you have a lot of data, you might avoid the equation. A third approach, that is the one which is still never really tested in data like the ones that I discussed now. We are working on that, but we don't have at the moment results that can be presented. That are stable enough. A third approach is an approach that tries to combine the 2 points of view that I just discussed. So it's an approach that uses data measured from the field, and also the fact that you're supposed to know what are the equations that drive that set of data. And what you do is you train a network So suppose this is an example by the group of Karnidakis, where a very simple example is a two-dimensional flow behind a cylinder, and you're supposed to have data only on the Lagrangian trajectories of a subset of particles. So you have a sparse data in X, Y, and T. So only if, as if you have anemometers that are advected by the flow, and you measure data only on the points of this particle. So how do you combine equations and data-driven tools? You train a network now that is supposed to be a global interpolator with a loss that also takes into account of your equations. So what you do, you train a network asking for any given time, time X and Y, to produce in output the data that you have measured. So in this case, for instance, it was the concentrations or the temperature in the point where you measure, and also the variable that you do not measure. So in this case, it was U, V, and P. You're supposed to measure only the concentration along the particle trajectories. And then out of these fields that are produced by the network, you can perform a differentiation with respect to the input. So you also have a guess of what are the derivatives. So you can also estimate, in terms of the guess of the output of the network, you can estimate the error that you would commit if you impose that these outputs satisfy the Navier-Stokes equations. So at the end, you optimize the network, asking to have an output for the points where you measure close to your measurements, and also to have an output that minimizes the distance from the Navier-Stokes equations. In this way, you have a physics compliant, a Navier-Stokes equation compliant reconstruction of your field. How good this is, and how fast it converges, and if it converges at all when data are very complex, at the moment, I think nobody knows. So it's certainly promising directions of work. I realize that we have only 10 minutes left. So let me eventually make just a 5 minutes spot of the Lagrangian aspects, and then maybe we can have 5 minutes for further questions. The Lagrangian aspects that we are working on is slightly different. It's using data-driven or equation-informed tools. In this case, the example that I wanted to discuss, it is to control some Lagrangian properties inside a turbulent flow. In our case, we took a paradigmatic and complicated problem. That is the problem of shooting on a moving target, shooting on a flowing target. So the idea is that you have one single particle that is advected by the flow, and we know that the tracers advected by turbulence can have a very complicated trajectory. And then the question is, suppose that you have a small other robots, as swimming agents, which is also advected by the flow, and at the same time can slightly control its trajectory by changing some swimming direction. So this control function depends on a swimming intensity and on a direction. The question is, in the case where the swimming is not very intense, because if the swimming is intense, the problem becomes almost trivial. How difficult it is to capture my prey, to capture my target in an optimal time. So it's an optimal shooting on a moving target inside a turbulent flow. Similar problems have been also attacked by the group of Rahul, Jeremy, and collaborators recently. But when the target is fixed in the flow, here we are speaking about a target that has the extra complexity to be advected in a random way, in a turbulent way inside your media. For this problem, we are, now I don't have time, but it's just, a sort of advertisement. We are working on 3 different directions. The first direction is optimal control. So we are trying to apply in a systematic way global optimization tools, supposing that you know the whole trajectory, the whole environment, right? So suppose when you want to apply optimal control, you need to control the evolution of the environment during the whole duration of your searching episode. Then we are comparing optimal control, that when you succeed to apply, it is optimal, we, by definition, otherwise there is an error in what you have done. We compare the optimal control against some heuristic policies that are, on the other hand, based on local cues only. The idea is we would like to understand how much this kind of searching problems can be attacked by local information only, and how far local information only solutions are from the optimal solution that you can obtain. And third direction, but this is still ongoing, is on the other hand not only using heuristic policies, but using, as you can imagine, policies that are optimized by a machine, by a neural network, or by some reinforcement learning approach. I'm sorry that I don't have more time to discuss on these issues. I think it's good eventually to take a few minutes to take questions. And if you want, give me 1 minute to advertise one database that we are building up to put all our data, and we are going to be very happy if other groups want to deploy their data also there in the database, such as we can build up, benchmarks and validation data sets for the community. And then, okay, I have some conclusions that I think it's better to take a question than saying more words. Thank you very much. I'm ready for your questions.
Thank you, Luca. We'll take questions from the audience now. Do we have questions? Yeah. Yeah, so are there other questions?
The set is already online, or? Hello?
Hello, Luca, can you hear?
Hello, yes.
The smart turbulence data set is already online?
The smart data set is already online, yes. For instance, all the data that we have used to train the network that I show for the gap refilling are there. There are also other data sets that I didn't show now. And yes, it is already online. It is the advantage of that database is that data sets are documented. So it's not just data put there. There are tags. There are instructions on how to use them, and we are also developing. It's still not there, unfortunately, but we are developing interface API that such as to allow people eventually to use the data on our machines. Because I mean, so to make some data analysis on our machines. Because I mean, most of the time these data sets are terabytes of data, so it might be very difficult to transport, to download. If there are no other questions, I take 1 minute to make one final conclusion, one remark that I think it's important, especially if there are young people interested to enter in this data-driven game. I give my point of view, at least, which is biased, of course. Sure. My point of view is the following: is that the Turbulence community, we must be very, very careful in using these tools as they are, black box, because we miss a lot of systematic information about, as we already discussed, if you want, the robustness of these tools, the scalability of these tools. It's very difficult to guess, once you have a machine that works for one given data set, what will be the hyperparameters setups for if, increase Reynolds of a factor 10 or decrease Rossby of a factor 10 and things like that. I mean, those back of the envelope calculations that we can easily do when we need to planify a new direct numerical simulations on the basis of something that we already know in another phase space parameter points, we don't have, indeed, any knowledge on how to planify new machines to solve new problems on the basis of something that has already been solved. And this is something that is very important to have, which means that it's important that the community invests in doing a lot of work in having good benchmarks, good validations, good best practice on how to move for the kind of problems that we are used to be interested at.
Luca, we have another question.
Hi, my question is the initial GAN predictors that you introduced. So is there a way to stitch both of them? For example, if there is a portion of data missing spatially versus there is some other space where only one component is missing. And
yeah, sure. The system, the setup is such that you can easily combine these two problems. Yes.
so like given like both of these GANs, we can just use them individually to reconstruct part of them.
No, I mean, what I'm saying is that, I mean, you need to train a GAN for that particular configuration where you want to infer simultaneously spatial and component. I mean, you cannot use a GAN that, I mean, you can do it indeed if you want. I mean, but if you want to, you can use the two separate GAN to guess the two problems, to solve the two problems separately. But I mean, I guess that if you want to exploit the correlations and information, it would be better to train a GAN that guess the two simultaneously.
Other questions? I'll ask a question. So Luca, you showed these large scale structures in your frames, right? You had these coherent vortices, but are you able to reproduce the small scale structures, dissipative structures with this machine learning procedure?
Say it again, I missed a few words, sorry.
Hello?
Yes, I missed a few words.
The frames that you were using to train the neural net or the package, right? So you had these coherent structures and those were being very well captured. But if you plot the dissipation, would you be able to capture the dissipation structure?
Yeah. I didn't show, it was one of the slides that I jumped, but you can do two things. You can just train, as I did, on the L2 norm of the energy, right, of the field, and plus the adversarial part, and then you ask how good it is also in reconstructing, for instance, gradients statistics and gradients point to point, and of course the gradients are reconstructed less accurately, but still better than or mean similarly to the, indeed in this case the gradients are better than the linear principal orthogonal decomposition, because the principal orthogonal decomposition are particularly bad at small scales because they do not have the adversarial part. So yes, the machine is definitely better, even relatively speaking, much better at small scales than at large scales.
Right, thanks.
Yeah.
Questions?
Continuing on the previous question, if the gap, you assume the gap inside the boundary. If the gap is outside, then of course extrapolation will be quite difficult, I guess. That will only be sometimes depending on where the gap is, particularly if it's a free flow field, free flow outside, and you assume the gap or the boundary outside, and you want to extrapolate, then it will be difficult. And the other thing is spatio-temporal. I don't know whether you are considering only spatial turbulence or spatio-temporal unsteady turbulence also. In that case, a training data set, would you want a training data set both in a spatial sense as well as a temporal sense?
Yes, thank you. The two questions are indeed relevant and important. I fully agree. If the flow is non-homogeneous, extrapolate, and if you didn't show in the training, then extrapolating on what happens in regions where you didn't show in the training, it will not work. I mean, it will work badly. Eventually, it will not work. First. Second, the temporal part, if the flow is non-stationary, which is the same of non-homogeneous, again, you can train it in the window of time when you have shown training data, it will work. When you want to extrapolate to times that has never seen, if it is non-stationary, it will not work exactly because it's an extrapolation in time. So this is, I think, unavoidable of any tool. Exactly, even the linear decomposition, as I repeat, if the two-point correlation diagonalized in a region, and then you want to apply these eigenfunctions in a different part of the flow that with a two-point correlation completely different, it is not anymore an eigenbasis.
Yeah, I think 2-point correlation should be at least you may expect 0.95 or 0.9 or something. If it is
Yes.
close to 0 or I mean less than 50%, then you may not get good result. If the 2-point correlation, spatial or temporal or whatever correlation you're thinking about. And the other thing is physics interaction. Do you mean to say that in any region, physics interaction can be resolved by real-time CFD and data optimization, real-time feedback control of data with to CFD and see nth degree, nth order feedback control.
Yeah,
system.
I mean,
Yeah.
I don't know if I understood exactly the question, but I mean, suppose I think you can combine the two. For suppose you think to nudging, you can use you know, data augmentation by a machine learning to guess what is the right to nudge or to guide the field, not only where you have measured, but also in regions where you didn't measure, because you have a first guess that is the one given by the output of your machine. This was my idea, but I don't know if this answered your question.
No, not that. If you have, say, in any complex flow, if you have multi-physics, locally there will be various physics, pressure gradient, thermal strains, gravitational field, magnetic field, so many things. Then can you really use these CFD? You can use make some reasonable prediction using all the physics. Assume you can resolve all the physics to a reasonable extent. Then, but if you have, as far as experimental data is concerned, it is not easy to resolve the physics locally, wherever there is complex physics interaction. So
Yeah.
can this be used to make at least resolve the physics and the different scales in different fields to a reasonable extent? Can real-time CFD combined with real-time experiment and feedback control, can it be used to resolve the physics to a better extent?
Yeah, I mean, this is in some sense.
I have a short question, which I got by WhatsApp, because someone who's watching online, Jay Kumar, he has asked, question for Luca. POD fails to perform well in isotropic homogeneous turbulence cases. How do the encoder and the adversarial approach perform in the isotropic homogeneous case? Because the data you use are apparently for turbulence generated by fixed rotating cylinders. Is that correct?
Yes, it is correct. Yeah.
Okay.
Well, it's for data generating with a rotating in a rotating frame. I mean, it's
okay.
Yeah. I don't know. I didn't try. I don't know. I do not expect. You know, homogeneous and isotropic turbulence. It's. I mean, the multi-scale aspect is even more important. I guess. But this is my guess, that the adversarial part would be even more important, and probably the mean square error is not going to, even for the machine learning, is not going to be very small, because it might be difficult to have a point-to-point reconstruction. But the real answer is that I don't know. I never tried, and I don't have a clear feeling about that.
Okay, thank you very much.
Okay, I think with that, we'll close the session. Thanks a lot, Luca. We'll meet here again at 4:30.